Okay, so let's start off with the big news of the year. In June 2020, the Fugaku supercomputer achieved the #1 supercomputer rankings on the four of the benchmarking tests. Maybe that's the first time. Top 500, HPLAI, HPCG, Graph 500, and this is also one of the greenest machines as well, up there in the top 10, which is outstanding for a massive system. So maybe you could tell me, how was it possible to do all of these things with one system? What do you attribute it to? And how did you come up with such a balanced design, Dr. Ishikawa?
Okay, so first of all, so I would like to say our goal is not to get the #1 rankings of those benchmarks. So our goal is to provide the world's highest level supercomputer environment to wide range application fields. And so that's why, so we have taken so-called code design approach together with application developers. And I think this approach, that results in getting #1 supercomputer rankings. So we got all of the benchmarks be the #1. And so in terms of the code design, so I have to explain the R&D the organizations, and also the what happened before the Fugaku development started. So may I explain this one?
Please.
Okay. And so actually, and by the way, and also I already sent slide decks, and the number, the beginning, that's corresponding to your questions number. Okay. And so first of all, let me show the slide 00 ISC. Before that, actually, let's see. Oh, can I show my slide deck? So it's disallowed. I want to share my slide. Who is host? Nish-san?
Yes, now you can do it.
Oh no, still. Can I? Okay.
Mm-hmm. Okay.
So by the way, first of all, so let me explain. No, before explaining our organization, but let me explain the benchmark results shortly. That because so we haven't used the whole machine node. Okay. In case of the HPL, that's can you can? Okay, so
yes.
Wait, maybe it's better to presentation mode. So switch to presentation mode. Maybe you can wait a moment. Ups. Wait. You see? And so the up and so HPL. So that's a Linpack. So we use the 96% node, and HPCG are 87%, and HPLI, in case of HPLI, just 80%. But the Graph 500, the only 55% of total nodes. Okay, and so those are the old nodes are used, but we got the #1 results of the both those the benchmarks. Okay, and so then so let me explain the how wait a minute. So this is the oops. So actually this was a presentation slide decks at the two years before. Okay, and so anyway, the RIKEN is in charge of the development of the Fugaku at that time. So the Fugaku name is not yet decided, and so we have been using the name post K instead of Fugaku. And and also okay, RIKEN AICS. At that time, our laboratory name was AICS, and that's why in this presentation slide, AICS appears. And so our laboratory is in charge of the development, and we have a contract with Fujitsu, and Fujitsu has been the designing hardware and also the key system software stuff. And also at that time, the ministry selected the so-called 9 social scientific priority issues, and also the 4 exploratory issues here. Maybe it's better to get here, okay? And so we have been taking the co-design approach to design CPU architecture, and also to develop application code. And so those 9 social and scientific priority issues, for those issues, the MEX also selected its organization. And so that means 9 organizations are involved with this project. Okay. And so we asked those 9 organizations to provide us the so-called target applications. And here. And so this is a list of target applications. So each organization provide us the one application code, and so we look at those source code, and then okay, so here, so those are representatives of almost all our applications in terms of the computational methods and communication pattern. Okay, and so what are the architectural parameters we must design? So this is a list. Okay, so seams length, number of seams, and the number of cores, and the number of NUMA nodes, cache size and bandwidth, memory technologies, and what kind of specialized hardware is needed, and also the interconnect and I/O network. Okay, and so also the sharing the applications, and also the sharing the design phase. So we mutually understand both the aspects. So for the computer architects, we understand the application behaviors, and the application developers, they learn how the architecture looks like, and what kind of the actual parameters are affected to the application performance. And so here, using the target applications, so we extracted the so-called kernel code, which is the hotspot in terms of the execution time. So and so this is a very small code, and so the running the such kind of the kernel code on FX 100. That was the latest the supercomputer in Fujitsu, and FX 100. The microarchitecture would be or extended to the Fugaku machine, though the instruction set is different, but the microarchitecture itself is coming from the previous the supercomputer. It's the FX 100, And so the profiling application behaviors obtained by running the kernel code on FX100. And then Fujitsu has the prediction tool to have the such the code will run on the designed architecture using the profile data. And then we look at which part must be the redesigned in terms of the number of those parameters, and also if the application code do not utilize those the architectural resources, that's due to the source code problem. Then also they fix the source code, and source code is changed, and also the architecture parameter is changed, and then we rerun the new kernel code on FX100, and then we predict the application code execution time using the profile with the new the architecture parameters. So this cycles, so many cycles are the running. And also in the case of the scalability, so we selected the TOF architecture, and so interconnect is also the successor of the K computer, and so the communication behavior was extracted running the application code on K computer. Okay, and so such a way, so we have designed the architecture, and also the application people redesign their the application code. And so back to the and then so back to the your question. So this kind of the co-design approach, using this approach, so I think the architecture is very designed in a balanced way to provide the computational powers to all of the applications. And actually, the Linpack, HPCG, HPL AI, and Graph 500, those are some representative of our application code. And so that's why we got the number one the ranking. So that's my observation.
Okay, would you like to share more about the components of the system and how they contributed the Fujitsu ARM chip with the HBM2? You mentioned the TOFU interconnect. There's a tiered storage system. Anything to highlight among the components?
Okay, let's see. So that's this one. So you can see.
Yes.
Can you see this slide?
Yes.
Okay. And so this is the chip. Okay. And and this is the die picture, and the CPUs, the memories, and interconnect. Those are integrated into this chip. Okay. And so here, so this is the silicon die, and the interconnect, the interface is equipped in the chip. Okay, and this is a PCI Express interface, and so there are 4 NUMA nodes. So here, so this is the one NUMA node. So 4 NUMA nodes are consisted, and each NUMA node has the interface for HBM2. Okay, And the using the silicon, THV technology, and so HBM is memory is in the next to the this chip and inside the this chip. Okay. And so we have the each node, so each chip NUMA node has 12 cores, and so we have four NUMA nodes, and that means 48 cores. Okay. And also the each NUMA node has one extra the cores. That's for OS activities. And actually, in total, the in terms of the number of CPU cores, we have 52 cores. Okay, right? Yeah, 52 cores. But the from the user's view, just 48 cores used. And so here's the interconnect interface. And each interconnect interface, this interconnect interface has 6 RDMA engines. Okay, and also it supports hardware barriers, and the network operation of offloading capability is also available. And here's the result of the low-level communication latency. Okay, it's achieved very low latency here. And skip to this one. And so, sorry, at that time, so we couldn't say the exact number of the compute nodes, and so that's why in this slide, just the over 460 petaflops. Okay. And so we have the two types of nodes. One is called compute node, and the other node type is called compute and I/O node. Okay. And so this compute and I/O node has the sorry, and so those are connected by Fujitsu TOFD, okay, interconnect. And so one of 16 compute nodes have one group. And so one of 16 compute nodes is a compute and I/O node. And that has SSD. It has about 1.6 terabyte. Okay, here is a picture. Okay, so those are 16 compute nodes, and one of the 16 compute nodes has SSD. Okay, and actually, so in previous slide, I said, okay, 2 or 4 compute nodes are used for OS activities in addition of the 48 cores. And that means so each compute node uses 48 cores for application and 2 cores for OS activities. And this compute and I/O node, this node, so 48 compute nodes are sorry, 48 the CPU core are used for application, and 4 CPU cores are used for OS activities. So 2 extra CPU cores are used in compute and I/O node. That's because this compute and I/O node has the services to file system. And so we have the 2 types of services. One is cache for global file system, and the other service is a temporal file system in the local file system and also the shared file system. Okay, and So this node and compute I/O node, compute and I/O node is the used as the first layer storage, and in the second layer, so we use Fujitsu FES. So that's the raster-based global file system, and so this is the overview of the Fugaku the hardware. And here, in addition of the main compute nodes, we have the several the nodes for servicing the users, login nodes and cloud storage gateway nodes, and so on. Okay. And the third layer, actually, so we have decided not provide the exact the third layer storage hardware, but so the user may use the cloud storage services from the internet. So here's the system software stack. The operating system kernel is based on Linux kernel, and so we use Red Hat Enterprise Linux 8 for user run. And in addition of the Linux kernel, so RIKEN has been developing the lightweight the kernel. So that's lightweight kernel. The provides the low noise and the special the runtime environment for HPC applications. And so a user may select Linux only or using lightweight the kernel. Okay. That's a selectable. And so there are the other the middlewares the RIKEN has been developing, and also here the programming languages are developed by the RIKEN. And here, so we provide the AI platform and the math libraries, and the compilers. Those are the supported by the Fujitsu, and also the tuning and debugging tools are provided by Fujitsu. Okay, and so we decided to use the open source management tool Spark, and now the Fujitsu and the RIKEN are testing the Spark, and actually the Spark was mainly developed for the Intel the architecture platforms, and so we must port some Spark packages. We must ported. That due to some packages, open source packages are just just for the Intel architecture. And so Fujitsu and RIKEN are now taking a look at the Spark packages. Oh, this is the current. This is not the current status. Maybe current status might be available. Is available using this slide. So taking this QRC code and then look at the web page. So this is at the last year's the results. Okay. So that's just a brief the introduction.
Okay. Japan is known for its energy efficiency focus and leadership. 4 of the top 10 greenest systems right now on the Green 500 are Japanese systems. So Fugaku and Micro Fugaku, the prototype forerunner, are two of the most energy efficient supercomputers achieving top 10 status on the Green 500, where all of the other top systems use some form of acceleration, a lot of GPUs. So how was the Fugaku design able to not only achieve the impressive flops per watt in the Micro Fugaku, but also to scale that into the 400 petaflops plus machine?
Yeah, actually, so your question is about efficiency and the scalability. And so for efficiency, the Fugaku microarchitecture is designed for high performance computing. So that means so cache size and out of order resources are not so large comparing with Intel chip. So Intel chip has the much cache and cache memories, and also the much out of order resources. And so thus the die size is smaller than Intel. And so this means the power consumption of the one chip is lower than the Intel chip. Okay? And also the utilizing the same SIMS length. So Fugaku's SIMS length is 512 bits. The Intel's one is also the same SIMS length. And so the Fugaku utilizes this SIMS resources, and so that's why the Fugaku achieves much higher the gigaflops per watt. Okay. And that's the efficiency. And for scalability, so as I already showed you, the TOFD interconnect is integrated into silicon die. Okay, and so also I haven't explained the new feature of TOFD, but in TOFD, message data is delivered into remote cache entry from a local machine. So usually the interconnect is using the usual interconnect. Usually data is delivered to remote memory, and if the program needs the data, then it always reads main memory. It's not on cache. But the TOFD feature is called cache injection. If the message has the cache injection flag, then so that data is injected into the remote cache. So that's the achieved the low latency. Okay, so that's another point is for achieving the scalability. Okay, that's all.
And Dr. Ishikawa, you have led various number of development projects from real-world computing partnership to the T2K OFP post-K feasibility study until the Flagship 2020 project was launched. How had this background helped you in the development of Fugaku?
That's Nishi-san's the question might be. Okay, and so I think maybe two points. One is the research and development view, and the other one is management view. And so in a research and development view, so my experiences on development of system software that include design and implementation of system software such as an operating system kernel, thread and MPI communication libraries, and programming languages. So I have written so many program codes of those software when I was young, and actually, so I'm still the writing a code, but anyway. And so those experiences helped intuition of software design, and so based on my experiences. So I can discuss design in detail with the developers. So, and so in terms of the management of view, I have been leading several projects you already mentioned. And so I have learned how I have to manage researchers as a project leader, not a boss. So in Japanese, the saying or proverb, so onaji kama no meshi o kuu. So maybe Denise-san can translate it, but the direct translation is, so we eat rice in the shared pot. This is a direct translation, but the meaning is different, of course. And the meaning is, so I think, so we work together and share all experiences, solving issues together and sharing happiness. So that's very important. And so officially speaking, so relationship between RIKEN and Fujitsu is the client versus contractor. But we run the project together. So that's so we like to share all experiences, solving issues together and sharing happiness. Okay, and so actually, so this is my motto. And so when the project started, that's the 2014. So there were more than 12 working groups and to design the basic features. So I attended almost all the working groups during the that phase. And so when this discussion was divergence, I like to conclude such kind of divergence. Okay, so that's all of the answer of this question.
How did the Fugaku development project form?
Actually, so history. So maybe it's better to show the some history, and so this project officially started the 2014, but so before that, so 2 years so-called feasibility study was run. And but before this feasibility study started, so we had the workshop to look at the future for finding the future supercomputer technologies and also the applications. And so this workshop is called SDHPC, Strategic Direction Development of HPC in Japan. And so at the first time, in 2010, it's just a kind of the grassroots activity. And then the following year, 2011, the MEX, the ministry, also organized such kind of activity, and we collaborate with that's the activity in 2011. And which one? This is 5. Wait. Let's see. And so this is okay. So this is a picture. What happened in 2011? Okay. So here's the government. This is the government, and so they have the 2 working groups. And here is our workshop. And so we collaborate with those working groups and preparing the white paper. Okay. So that's happened in 2011. And following this activity, then feasibility study launched. That's from 2012 until 2013. So 2 years. Okay. And then, sorry, it's not. And then, so this is a feasibility studies on future HPC and R&D in Japan at the 2012 to 2013. And so one team led by Tomita-san and Matsuoka-san. At that time, he was at the TITEC, and so they investigate the future and research roadmap of science roadmap. And here, so we have 3 system studies. One is done led by Kobayashi-san from Tohoku University with NEC. The approach is based on the vector machine. And Mitsuhisa Sato, at that time, he was the University of Tsukuba's professor. He led the accelerator technologies investigation. And so at that time, so I was the University of Tokyo, and I and Fujitsu and Hitachi and NEC, we studied the general purpose architectures towards exascale machine. And and after they are reporting those results, the RIKEN AICS, the currently the computation Center for Computational Science and Computational Science, so RCCS. Anyway, so RCCS selected the those architectures. At the first time, actually, the Fugaku, the CPU node, Fugaku node has the 2 types of CPUs. One is the general purpose the CPU, and the other one is the accelerator. So that's based on this team's result. Okay, and so then back to your question, and so sorry, I haven't sent this. You can see. I haven't sent this slide, but so this is a formation. And so after the feasibility study finished, so I moved to the RIKEN and as the project leader. And so Sato-san also moved to the RIKEN, and he became the leader of architecture team. And so Tomita-san, so at the time, he already at the RIKEN, but so he became the leader of application development team. And also we invited the Makino-san to be the leader of co-design team. But that's actually, so co-design activity is done by this Sato-san team and the Tomita-san team. And Makino-san team is actually the developing the domain-specific library. And also, so we contracted the Fujitsu and contracted the other vendors for developing system software. And we have the Japanese collaborators, and also we have the international collaboration. Okay, so this picture I have to send it, but this picture gives you how the organization looks like, understanding. Okay.
What was the biggest challenge in the development of Fugaku?
So next, what are the so you said the biggest challenges?
Yes.
Yeah. So actually, the biggest challenges was actually the prediction of long-range hardware technologies. So as I already explained how the project was started, but the key point is the budget and the goal of performance was determined at the 2013. Okay, that's the 7 years before. And availability of expected technology, I mean especially the silicon technology, was delayed. So so we expected 10 nanometer device technology for high performance market. But so that would be available in about 2017. But actually 10 nanometer device technology was available, but it's not for high performance. It's for like the smartphone, low energy, the embedded system. And so the production failed. And so there were two ways at that time. So we considered. So one way is using the available technology in order to meet the deadline of deliver. So we set up the deliver date was 2020. Okay, and or using the next technology, and deadline of the delivery is extended. And so that's the and then so how the challenge was the delay of machine delivery is how shortening as much as possible. And also at that time, so we thought what kind of additional value could be implemented because we will delay of delivery. And so it was a chance to introduce new features in the system. So one of additional values actually is supporting half precision floating point operation. That's used for AI workload. Okay, and so that's the biggest challenge.
And the US and Europe are also working on exascale projects and bringing exascale to fruition. Is there any cooperation between Japan and the US or Japan and Europe? And is there a difference between the Japanese efforts and those in other countries?
Oh, yes, yes. We have been collaborating with DOE's laboratories. That's under the government level agreement. So some slides. So I already sent you such kind of explanation. So please look at the slide there. And also we will also have the collaborating with CEA. That's the French the laboratory. And collaboration with Intel in operating system research field is also doing. Okay, and other the collaboration, I think the some slide has a list of the collaboration the organization. Okay, and so I'm not sure about their formation and the differences between our project and the other projects. So I'm sorry.
The US and Japan are collaborating on the COVID-19 research. RIKEN, RCSS, is part of the HPC consortium, and it was announced that Fugaku was put into service early, put into production early to find answers for COVID-19 research. What is your perspective on the role of high-performance computing to support these most consequential grand challenges?
Okay, and so that's actually, so I think the role of the HPC is so the accelerating sciences using simulation and AI technologies running on the supercomputers. So that's it, I think. It's just a tool. Okay.
What do you think of the so-called race to exascale, as it is sometimes described in some media channels and elsewhere, between the various geo regions, the US, Europe, Japan, China? How do you conceive of the term exascale computing, and do you think it has usefulness?
Actually, so it's actually so so first of all, so I do not like the word race. Okay, so actually, so this is not a race, but anyway. And so the exascale computing was just one milestone at the year around 2012 when K and Sequoia achieved over 10 petaflops. So to make the next R&D plan, so the US and Japan were thinking of the how much the how the next machine would like. And of course, one is it's the step-by-step approach. The next the machine would be the 100 petaflops at that time. But so it was supposed to easily realize such a machine without running a national project. And so to launch a national project, it required much challenging the goal. And so at that time, the exaflops, that's the 100 times faster than the machine at that time. And so actually, so I think the exascale is a kind of exascale computing is a kind of the just buzzword, but this mean was so we need the research leap. So that's it.
And are you thinking beyond Fugaku? What requirements are driving the next round of innovation?
So actually, so I've been spending time for the stabilize, make the hardware and software stable, and I haven't had any time to think of the next machine, next one beyond the Fugaku. And so young researchers and I have already started to think of the next machine. Maybe it's better to ask them, and they organize the same the workshop which I have done.
Do you think it is possible that Fugaku will be expanded or possibly use a next generation Fujitsu ARM A64FX chip or whatever it is called at that point?
Fugaku itself, do you mean the Fugaku is extended?
Yes, do you think you would make Fugaku bigger or upgrade?
In terms of I think the in terms of the capacity of the computer room, it can be, but how we can get the budget.
Mm-hmm. Okay, and then let's end here with the reason that we do all of this supercomputing. We'll come back to applications, both for Fugaku and for future systems. What are some of the most important application areas and target workloads from Japan's perspective or RIKEN's perspective or from your personal perspective? What are you looking to be able to do with the coming computers, with Fugaku and the coming generation of computers?
Actually, so what I can say is just for Fugaku, not for future systems. And also this is my perspective, not from the Japan nor the RIKEN's perspective. Is this okay?
Yes.
Okay. And so back to the main goal of our project. So Fugaku was designed for mainly running applications related to 9 priority issues. And so personally, I would like to see those results using Fugaku as soon as possible. And especially so ensemble simulation with big data simulation. This is one of the application area within the 9 priority issues. So this the ensemble simulation with big data simulation is so that's the I also involved, and so I'm much interested in how the this research group will deliver the good results using Fugaku.
Okay, great. Thank you so much. Thank you for doing this interview.